Hello, everyone. Welcome to our webinar for today. Our subject this week is autonomous vehicle acquisition. We're going to be talking about the SimCenter Scapter. Today, we have a special guest actually with us, too. I'm going to be presenting along with two of my colleagues. I'm going to allow them to introduce themselves. Tony, would you like to go first?
Sure, thanks, Charles. Yes, my name is Tony Uchis. I am a portfolio development director of Autonomous Americas. So anything to do with really automotive safety or vehicle safety, could be a plane, a vertical takeoff and landing safety. I'm in charge of that for Siemens in the Americas. I have a long track record being in automotive safety. I actually started the very first automotive algorithm company in 1992, a long time ago. So sensors and algorithms and data acquisition was always an issue for me. So some of the sensors I was working on in the early 90s had data rates that were much higher than other sensors. And so I was always trying to find the best data acquisition systems that would help me. Of course, now the rates are even higher. So that's what we'll be discussing today. Thank you.
Great. Thanks. Looking forward to hearing more about it, Tony. Scott?
Yeah, hi, my name is Scott Beebe. I'm an application engineer on the test side of the business along with Charles. And so Tony's going to be talking more about some of the virtual side and the predictive measures with autonomous vehicle acquisition. Charles and I will be talking more about the kind of physical data acquisition as it relates to the sensors on the vehicles and correlating that data and making sure the right decisions are being made based on the interpretation of that inflowing data.
Great. Thanks, Scott. Well, as always, during the presentation, please feel free to type questions into your questions panel on the webinar control panel there, and we'd be happy to reply. Scott and myself, as well as Tony, will be monitoring that, so don't hesitate. As well, after this webinar is over, you'll get a copy of all the slides that are going to be presented, as well as a link to the recording of this webinar so that you could review it again if you need to, or share it with your colleagues. Well, with that, why don't we go ahead and get started and take a look at the agenda for today. So we're going to first start off with a little discussion about the background and motivation for this webinar and the idea of autonomous vehicle and related to safety. Then we'll move into talking about some considerations with regard to acquiring data and the different sensors we use. We're going to specifically focus on radars, ultrasonic sensors, LiDAR, and video cameras. And I think at the end too, we have some very interesting stuff that Tony's going to share related to using simulation to virtually create different scenarios to expand on our testing. Well, starting off with the background and motivation. This is a chart that some data from Europe, some European data. Basically, it shows the number of deaths and traffic accidents over a number of years. And you can see they have a target as well as the actual road fatalities. And it was decreasing at a nice steady rate in line with the target. But you can kind of see things kind of plateaued a bit. And the decrease was certainly due to passive safety measures such as seat belts and airbags, ABS, traction control systems, and whatnot to mitigate the consequences of an accident. But it became clear that to gain any more improvement, there was going to need to be something else, so some active safety measures to prevent accidents as well as the passive measures. So that's where ADAS kind of came in. And turn on my pointer here, which this acronym stands for Advanced Driver Assistance Systems. So that could be things like automatic braking or lane keep assist. Maybe some of you have these systems already on your vehicle. So that is one step towards preventing deaths from accidents, but as well, many of you probably know there's big work being done right now in autonomous vehicles as well. So completely full robotic taxis, basically. And we can kind of classify it. The SAE came up with these, well, there's 6 categories, but I guess it goes from 0 to level 5 of ways of defining different levels of automation. So level 0 being no automation, just regular driver, right? Driving, just driver only, all the way up to level 5 where it's full automation, like that robo taxi, maybe that dream you have of falling asleep in the car and waking up at your destination safely. We're not quite there yet, but we're working towards that goal in the industry. And a lot of vehicles do
I'd
have
say we're
like,
firmly in the level 1, Charles. Wouldn't you agree?
yeah, yeah. I would say, I
Yeah.
mean, a lot of vehicles do have the auto cruise and automatic braking, lane keep assist, things like that. But as you can see too, I would think you agree, guys. The sensors required to reach level 5 is, as you can see from the graphic here, it steadily goes up, and that's some of the things we're going to talk about. Is the process of getting to level 5 at some point in the future down the line, and what type of sensors we need to be able to achieve that goal and capture that data. I guess along the way too, we should talk about the development process. A lot of times when we talk about vehicle development, software development, you may see like a V diagram for the development process. Where here it's more of a, when we talk about autonomous vehicle development, we like to think about it in this closed loop process. So we would maybe start here in the virtual side of things, developing our sensors, our vehicle, our algorithm, verifying how things are going to function virtually, doing some certification work, and then we would move into physical testing of the systems that we develop. By deploying it into the field, we would monitor how it behaves in different scenarios. Inevitably, there's going to be perhaps scenarios that the vehicle or the sensors don't interpret correctly. So we need to diagnose those, and then we go back into, once again, the virtual development cycle to make further improvements. And this is where we kind of talk about things today, or Tony's really going to focus on this pre-scan 360s kind of family of products that kind of handle this virtual side, the development of autonomous vehicles. And Scott and I are going to focus on what happens on the physical testing side, where we use our Scapter solution. And if you're not familiar with Scapter, hopefully you will be after this presentation, but kind of stands for sensor capture, right? Capturing data from all these sensors that are utilized in autonomous vehicles. And talking about a little bit more about the sensors that we need to use and why so many. If we take a look on this side of our diagram here, it kind of highlights the challenges that we see. Like when you're out on the road, there's obstacles, that could be people, that could be potholes, different events, vehicles turning out in front of you, there's traffic signs you need to read and obey, changing road conditions with weather perhaps. And to be able to deal with all of these obstacles, we use different types of sensors, from cameras, radars, LiDARs. We use the CAN bus to communicate all this information between the algorithms in the vehicle that are making decisions based on that. And all these sensors together helps us to perceive what's going on around the vehicle and on the road. And then we can plan action for the vehicle to take. And once we do that, basically we're talking about controlling the vehicle, be it a steering input, braking, whatever the case may be. And to kind of give you an example, I have a video here that highlights some of the perception data that you would be able to acquire from all these sensors and what it needs to do, such as reading the stop sign there, noticing the vehicle that's in front of it, staying within the lane as it's going down the road, making turns, understanding the best route. So all of that perception is going to be coming from the data that we acquire from our cameras, our radars, our LiDARs, etc. So it's quite a big job, in fact. And I say that not just because of the amount of work in developing it, but literally it's huge amounts of data. Because the slide here, we're talking about collecting raw data, uncompressed, and we'll talk about this later, but the number gets really big fast when we're collecting all of this data. I guess we'll let Scott maybe touch on a little bit of that too, about the acquisition and the sensor considerations at this point.
Yeah. So yeah, so some keys to some of the things that Charles said is you have this data explosion. Just like he mentioned, there are all kinds of sensors, and the further we go up those levels that he spoke about, once we get to that level 5, there's quite a few sensors that are going to be needed, and they're going to be multiple types of sensors. So you have this multi-sensor infusion, and all of these sensors need to work together and communicate together in order to be able to make the same type of decisions as a human driver. With all these different conditions, there's certain sensors that work better in low lighting, rain, different interpretations of, stop signs and things like that, and some of the things that we'll even look at in more detail. But we'll have this multi-sensor infusions between cameras, radars, lidars, and other things. And ultimately, from the perspective of acquiring this data and looking at it, that's a lot of raw data to bring in, and we need to make sure it's time synced, uncompressed, unimpaired. We want to see the data as it's actually being acquired. And this will allow us to do this accelerated validation. We can look at that data, we can see what's going on physically and bring that physical data into, back into that infinity loop that we had, where one side was for the pre-scan, the other side is for the Skapter testing. We can take that test data, bring it back into those pre-scan models, look through it, improve upon those algorithms, and eventually move to that level 5 that we're shooting for. But if you think about the amount of data that's coming in with these high resolution cameras, these LiDAR, radar, sensors, and everything else, it's just a huge amount of data that we want to make sure is time synced and brought together. Go ahead, Charles. Charles is controlling the PowerPoint we're sharing here. So yes, we have the SimCenter Skapter recorder, and this is the physical piece of hardware that we're referring to. So it has a large amount of onboard storage. As you can see here, it's 32 or 64 terabytes. That brick there on top, and you can actually see the word where it says brick storage, that's essentially the memory disk, and that has the ability to be detached from the system. So you can get multiple brick storage units, and you can acquire, say, an 8-hour shift driving, take that brick off, put a fresh one on, and get more data while that data that was previously taken is being ingested, analyzed, and used. This system is designed to get the time synchronization that we're mentioning. So we want to get that time synchronization across all of the sensors as it's collecting that data and as we go through different driving conditions. It also timestamps the data. So if you want to mark specific events, then all of these sensors are timestamped together. And we can say, I want to look at all the left turns taken during this 8-hour drive shift. And we'd be able to do that with this system. So here's an example of, just a handful of sensors that could be used in an autonomous vehicle or a vehicle that's being developed for autonomous driving. You may have seen these either through news articles or different cities where they're actually working on these, but you'll see kind of this rack mounted with different sensors, and there might be a radar, LiDAR system on that. You can see there's a couple different types of LiDAR systems. There's solid state LiDAR, there's scanning LiDARs and pulse system LiDARs. The cameras and radars, those are different ways of also interpreting visual information to help the car make decisions like we've been talking about. And the real challenge here is how do we get all of these different sensors recording and communicating that we can look at it while it's pulling in information. So with the Skapter system, what we want to do is kind of bring this all into the same system, all into the same language. And this would be kind of a basic setup where we've got, maybe 3 radar systems and a LiDAR. And so I can bring all of these into the Scapter under an Ethernet communication, directly plugging these into the system itself. And so this is kind of a basic setup as an example. And we'll kind of keep coming back to this slide and show you as the sensors kind of expand and get more complicated, how we bring those all together to time sync the data. But this would be a basic setup where I could use the Scapter to start recording these 4 sensors. So if we talk about radar and some radar basics, we're gonna look at some of these different sensors and some of the strengths and weaknesses that they have. Radar, as you can see here, uses a radio detection and ranging, and so it will send out this radio signal, and that's the incident signal, and the reflected signal then comes back for interpretation. It'll give us kind of some relative distance in size and show us where that potential obstacle is in relation to the vehicle that we're driving or testing is. For example, this is used a lot for adaptive cruise control, where we can see how far that vehicle is in front of us. We set a distance for that adaptive cruise control of how many car lengths we want, and then the car will adjust speed to keep that distance from the vehicle in front of us. Okay, so here's kind of the radar pipeline. We send out this waveform, this radio waveform, and then that comes back. The signal's processed. We have those algorithms within the vehicle that determine what that information means and what that relative distance between an obstacle might be. And then that's communicated to the vehicle, and then the CAN data and things like that will control the braking, will control the acceleration using that communication protocol, and then the vehicle is controlled. So just an example of how that radar model works.
So one thing to point out here as well is, if we go back a slide, one thing to point out here is, again, the waveform's transmitted, it's mixed with itself. You then, after the beat signal, that's where you have raw radar data. So that is the data. If you looked at it, you put it on an oscilloscope, it'd just be a bunch of sinusoids. You wouldn't even really be able to tell anything. So what you need to do in the sample algorithms part there is to do a 2-dimensional FFT. So the 2-dimensional FFT, next slide, please. The 2-dimensional FFT is going to give you data in both range, as Scott was talking about, but it also gives you Doppler. So what is range and Doppler? Okay, range is obviously what it says. How far away is the object, okay? And then Doppler is what is the speed of objects relative to you in the longitudinal direction only. So it does not pick up perpendicular speed. It only picks up speed relative to where you're going. So when you look at a range Doppler, what you're doing is seeing how far away, but also how fast things are either moving towards you or away from you. So in order to get to that, you have to do this 2-dimensional FFT, so that you see that on the bottom left where we have a range Doppler as time is going on, and those dots more in the top are coming from the vehicles, and that cluster kind of at the bottom left are everything in the scene not moving, okay? Now, you can process those and make a more complex system by using 4 receivers in a linear array and then making a polar map, and that's what you see on the right. So there's a lot that can be done with radar, but let's see a situation that we looked at that really happened in the real world, but we weren't sure why it happened. So next slide. All right, so this is going to be a movie. And what we'll see in this movie is from a actual vehicle, a Tesla 2016, so this is real. You'll see a camera and you got a car in front of you, and somehow we stopped in the Tesla, even though we couldn't see the car in front of that, right? So the Tesla saved an accident from happening. Now, how did that happen? Well, we looked at it and we knew that it had to be the radar, because the camera, you couldn't see the car in front. So how did the radar do it? So what we did was we created a simulation of it. We figured out the radar was a Bosch. We put in the parameters and went about the process of trying to figure out how it did it. And what we did was, now you see the range Doppler on top, and can you pause here? And it just disappeared, but that's okay. So you'll see that we have the red car in front of us producing the dots that, you see the red dots in the range Doppler plot, and that the blue circles, there's dots there right now for the pause. It's not, but they are there. Trust me. So
And I think we muted you.
how did the radar get those dots? Well, because we could simulate it, what we're able to do is figure out that the radar signal went under the red car, which was in front of the Tesla, bounced to the next car, came back under, and back to us in the Tesla. And right now what we see is that the blue car and dot is pretty far away. Range is the x-axis, and so that's pretty far away. And the two sets of dots, so the blue dots and the red dots, are near zero, which means they're going about the same speed as us. And now when we start the movie up again, watch what happens to the blue circle of dots. They're going to come down and to the left, which means they're getting closer, and they're going slower than we are. So if you could start it up again. And so what you'll see, here they go, okay? And what happens is, in the Tesla, the algorithm saw dots that we're getting closer to, and they're slowing down, therefore we got to stop. So by shooting the signal under the car, we're able to see in front of the other car. So pretty cool thing, and we were able to figure it all out. Okay.
There you go. So yeah, so this was a slide that Charles and I will continue to kind of come back to. But when we talk about radar, based on some of the things we just discussed, you can see its strengths here are depth perception, its independence from daylight and weather. It's good with distance and velocity. So there's some strengths there with radar. And we'll talk about some of these other sensors as well. One sensor that is sometimes maybe confused with radar based on its ability to determine depth is, if Charles goes to the next slide, is this, I guess here's maybe something to talk about first before I talk about that. But what percentage of vehicles in production have LiDARs installed? So not radars, but LiDARs installed.
So we want to hear your opinion. We'll launch a poll for the audience to participate.
And we have both extremes here as choices. It's either 99% or less than 1%. So
okay, we got a little bit over 50% of the people have voted, 70%. I think I'm going to close it right now and share the results for you, Scott.
all right, let's see it. So it's pretty good. So I would say that 2/3 of the participants are right on the money there. It's actually less than 1% of the vehicles today have LiDARs. And it's, it's easy to think that it's maybe more vehicles, and that's kind of what I was alluding to. A lot of people, well, we're still not quite to that slide. I'm out of order here, Charles. But here's what's, and this is, let's see, a lot of these are in German, but if you look at the smaller font underneath, kind of where Charles is highlighting, you can see the English version here. But here's a Audi vehicle and all of the sensors involved in terms of helping with ADAS systems. You can see there's quite a few sensors and a lot of different kind of sensors. There's quite a few cameras. There's radar, but there's actually no LiDAR sensors on this vehicle.
No, actually, I think this is the only production vehicle with a LiDAR at the moment.
Is it? Where's? I was looking for it and I can't find it.
Yeah, it's just we don't speak German very well, but I'm pretty sure this is the only.
Because I
production
see
vehicle with a
what's
LiDAR.
often confused as a LiDAR, which is that ultrasonic sensor. The ultrasonic sensor is a sensor that uses actually sound at a high frequency to determine proximity. And you can see these sensors on a lot of vehicles today that help with backing the vehicle up. Some of them have it on the front bumper for pulling into a garage or parallel parking to see that vehicle in front. And the ultrasonic sensor, like I said, uses a high frequency noise, higher frequency than what we can hear as humans, so that we don't constantly hear these ringing tones to determine the depth or proximity of the vehicle to an object. And they're obviously very good, independent of daylight. They work well at night or on a bright morning. So those are great sensors that help with proximity as well.
Okay, another.
Go ahead, Charles. I think you were going to take the lead there.
Yeah, a LiDAR is a pretty popular topic. I guess maybe some people in the audience, I think, are aware that maybe this wasn't always Elon Musk's preference for autonomous vehicle sensors. He didn't really like LiDARs. And we'll come back to that radar diagram in a second and talk about the strengths, but just wanted to show you an example of a LiDAR system. And that's just an acronym. Stands for light detection and ranging. And basically, oversimplification here, but it's just sending out a laser, right? And it gets a return, and based on the flight of time from the return signal, it can get a depth, and it just scans across an area, right? To basically map where an object is, how far it is, and basically its size as well, where it's located in the space. And some examples, maybe you've seen them on some vehicles, these scanning LiDARs on a lot of vehicles that may be involved in autonomous vehicle development. They're quite large, lots of moving mechanical parts. So you can imagine this would be difficult to package in a vehicle and expensive and probably not too robust with that design. So what has happened in the industry with advancements in LiDARs is the solid states, where they've kind of basically simplified the system and gotten rid of all the moving mechanical parts that were here used to move this laser beam around to scan an area. With this solid state, we don't have those moving mechanical parts. It's far more robust, and obviously you can see the size as well. It's an improvement for packaging standpoint. And when we talk about LiDAR, some of the considerations we have to think about is, if you see this image, we have an image of a vehicle that's painted black and a vehicle that has red paint. And we can see that laser energy has a difference in energy reflections because of the black absorbing more than the red. So that's a consideration that we have to deal with LiDAR. Here's an example of what we would call a point cloud. This is the data that we would get from our LiDAR scanning the environment. And just, I got a still picture here, so it moves pretty fast, kind of hard to see what's going on. But as you can see, our LiDAR is able to identify people, buildings, vehicles, as it's scanning the environment as this vehicle is moving down the road.
So what LiDAR, I just want to make a quick comment here.
Please do, please do.
Key features of LiDAR relative to radar, and it's, you know, in your little graphs there, is what's called azimuth resolution. Okay, you can see resolution there. Resolution generally means azimuth, so that is, let's say, latitude or perpendicular. So the resolution that it has is much greater than what radar. Now, radar is coming up. There's some new radar coming out that's going to try to get closer to what LiDAR resolution has, but they're not out right now. The radar that's in all the vehicles, which is much more than 1% of the vehicles, by the way. it doesn't have that kind of resolution. So just wanted to comment on that.
No, it's a good point. Thanks. And now another sensor that we would see a lot with autonomous vehicle development is cameras. And obviously with cameras, if you look at our radar diagram, there's some pluses here. Good for resolution, but maybe daylight independence. We could see that could be a problem for a camera, right? Using it, it's not as accurate at night. But classification is very good. We can clearly recognize people and other signs easy with video images. And some considerations though, when we're talking about using cameras with our autonomous vehicle acquisition is some of the things we already talked about. The huge amount of data, like these cameras that acquire raw data. Basically, usually there's two formats, GMSL2 and FPD link, and they're just serial cameras. The data is serial. And what we need to do though is to be able to timestamp it and sync it with all the rest of the sensors. We use the IEEE 1588 protocol for time synchronization. So we have to get them into Ethernet packets. And that's what this Sceptre MDI link does for us. And another thing you might notice, we have different interfaces kind of distinguished by the color of the connection to the Sceptre. And you see this is a 10 gigabit Ethernet connection for the cameras, right? It needs to be very fast. And another point with regard to synchronization is this Sceptre MDI link is located external to the Sceptre recorder, so we can get it closer to the camera so that we can timestamp that data sooner when it's coming into the system, even for the vehicle, for that synchronization purposes, to get it down into the nanoseconds of synchronization between all of the sensors utilized. And if we kind of dig into the camera components, obviously the physical components of the camera, the lens and whatnot, play a role in the quality of the images you get. But there's also, in some cameras, you have these ISP, image sensor processing board, which also plays a role into improving the quality of the image. One example would be for exposure. If we look at this image here, this is what we consider correct exposure, but you could have a situation where it's underexposed or overexposed, and our ISP board can help in that situation. And maybe from this image, it doesn't look so critical, but we have an example here that maybe Tony can walk us through to show why that exposure can make a big difference in this scenario.
Yes. Okay. So if we look in particular at the bottom right image, and you see the little arrow pointed there, you can see a person in that little circle fairly easily, and that would be one way to do that. That data, let's say, is something generated where we generate red, green, and blue imagery. So we can see that, okay? That's great. The problem is that's not really what a camera does. It doesn't really output that. A camera has sort of a optical density function that's not necessarily red, green, and blue, and it's something called a Bayer image. So that would be on the right side. And what we see is a difference when we look in that area. It's tougher to see, but also look at the little circle of the lane line, how much of a difference there is. In the red, green, and blue sort of perfect image, it looks nice. But if you go over to the right, we see it's kind of choppy and not as nice. The image on the right is what comes out of a camera. The image on the left is not what comes out of a camera. So you can see it's very important to make sure that when you're collecting your camera data and then you want to simulate, that you simulate what the camera is outputting, not something, that's not that. And that's really important.
Thanks for those details. Appreciate it. And Tony's going to show some more stuff with regard to simulating these autonomous vehicle situations a little bit later. Just some quick basics to kind of drive home a point in a moment. But this is just an example of the smallest part of an image, right? Pixels, right? This is a 41 by 24 pixel image. And we're just, this being one pixel here, for example, or just defined by a position and a color. And what do you think, Scott? What do you see there anyway in this? What is if I put all these pixels together, looking at them together, what image do you see?
It looks like an eye, a
That's
person's eye.
that's exactly what it is. Do you think that's enough pixels for a autonomous vehicle acquisition for you?
I wouldn't want my vehicle making driving decisions based on this image.
Okay, so we do have the capability nowadays to have higher resolution images, thankfully. Everything from HD to Ultra HD, that's 4K. Maybe you guys got some 4K televisions. I don't, I want one, still fighting with the wife. Which would you prefer for your data acquisition, Scott? Which resolution you want to go with?
I mean, if it's determining how my vehicle's driven, we want 4K. If I want to
Okay,
watch 4K for TV, I want it for my car.
okay, all right. Now this is two images demonstrating bit depth, right? And we're just talking about, like, the human eye, I think, can maybe see around 13 million different colors. And when we talk about bit depth, if you look at these two images, do you notice a difference, Scott? To you? I'm just picking with you, sorry.
Yeah, no, most definitely. I mean, you can tell a pretty big difference in this bit, right? Is this 2 to the 10th and 2 to
The
the 8th?
term that explains this is called dynamic range. And that, when you have 8 bits, you have a dynamic range of, well, 255, whereas with 10 bits, of course, you have 1024. So you have a bigger dynamic range, and so you don't end up getting those kind of swirls in the sky,
Right.
because you don't have that dynamic range.
Yeah, exactly. So bit makes a difference in our images. What about frames per second? Kind of in our little animation here, 60 frames, 30 frames, 50 frames. If you have a choice here too, what do you guys want to go with for your data acquisition frames per second?
I'm going to stay with my same theme and pick the highest rate here.
Okay, yeah, I see that high quality stuff you're going after. Okay, great. And this all leading to a point. But real quick, just incidentally, just for, trivia's sake, what do you guys think? How many frames per second are used in movies? I guess I will ask the audience as well as you and Tony, via a poll. Does anyone know any movie buffs out there? Okay, we got about 30% of the people responded. And I think I'll just close this one a little bit sooner than the last. So we'll close it and I'll share the results. So I can't see the results yet. So you guys guessed correctly. 24 frames per second actually is what are used for movies in general. So good job. Real
quick on that too.
Sure.
If it was a higher frequency frame rate, sometimes if you look at movies, and you certainly, I'm sure everybody has done this, where you go through a tunnel where it looks like the wheels are either stationary or going backwards, and you could see that in movies too, like especially some of the old westerns. It looked like the stagecoach, the wheels were stationary or moving backwards. How does that happen? And that's a function of something called aliasing. And so if the frame rate is higher, you don't get as much, the chance of aliasing is less. So another reason, Scott, you picked correctly when you said 60, you reduce the effects of aliasing as well when you do that.
Good point. Smart cameras. So we were just maybe talking about, I would say, general cameras used for autonomous vehicle acquisition and ADAS systems as well. But there's also smart cameras, with the difference being that not only are we still collecting the raw serial data and time stamping it and putting it in Ethernet packets, but we also, with those images, have a camera that tells us what it's identifying in the picture. Like it could be a speed from a sign, or an image of a person or a vehicle. So smart cameras. Tony, what is the kind of the trend right now with, I guess, autonomous vehicles? Are more smart cameras now being utilized more than regular cameras? I mean,
Oh yeah, definitely. Well, not more than regular, because for example, the rear cameras, those
mhm,
have really no processing or very little processing.
okay,
The smart cameras are used more for things, looking forward. Mobileye is a big company in that space. You got a Mobileye up there. But if you were to look at, regular cameras are used more right now because we still rely on the driver. So just give the driver a view and let
okay,
the driver do the processing.
good. So Scott, now it's come time to pay the piper, right? You made a lot of choices there. You wanted a high resolution, right? I think you
Right.
went with the high bit rate. All this leads to a bigger image size. You also said you wanted really high frames per second, right? So if we just step through an example here, and let's just use this 356 megabytes per second as an example. And let's say, in general, maybe you send your drivers out to go get 8 hours of data in a shift. And if we do the math on that, right? 8 hours, and there's 60 minutes in an hour and 60 seconds in a minute, that's almost 29,000 seconds, right? And we multiply that by the 356. Basically, at the end of the day, for one camera, we could get approximately 10 terabytes of data. So that's quite a bit. It's quite a bit. So you could, what'd you say?
So that's a ton of data.
Yeah, yeah. So if you saw the 32 terabyte and 64 terabyte cartridges that we offered and thought that was a lot, maybe this changes your perspective a bit. It adds up fast.
That's right.
Here's a little picture behind the curtain there of those cartridges that we use for recording the data. And coming back to this radar plot again one more time, I think one drawback to cameras, which maybe we didn't quite touch on, would be depth, right? We can't tell depth with the picture. Well, it has great resolution and we can classify things easy, like with those smart cameras. It's a person, it's a dog, it's a car. There's obviously some drawbacks with the cameras.
Although there are stereo cameras,
Mhm.
Suzuki's a big proponent of stereo cameras. Some other companies, not too many, that
Yep.
can add in depth. It won't get or range. It won't get the same results as, let's say, ultrasonic or radar or lidar, but
Mhm.
it definitely lifts up that depth on camera when you use a stereo camera.
Okay. Well, there are some options. And I guess the whole point of bringing it up with the radar plots here is that really probably not one sensor is ever going to be perfect at this point. Maybe somebody will come up with something in the future, but right now there isn't one sensor that we probably say it's perfect for everything. So we end up having to do a fusion of all these sensors to kind of capture all of their best qualities to be able to have the correct perception data for our ADAS and AV autonomous vehicles to make good decisions. And I guess I'll let you talk a little bit more about how things work with the fusion of all these sensors.
Sure. Yeah. So this is that MDI link that you mentioned earlier that is used alongside the cameras and bringing that data into the Scapter unit. And what this does is converts that camera data to Ethernet data. And the nice thing about that is those Ethernet packets then can be time stamped. And the Scapter system uses IEEE 1588, which is a time stamping certification that keeps things together. So it brings that camera in, and you can see it converts it to the Ethernet packets there. It has the redundancy check, and then brings that into the SCAPTA at a high gigabit rate, 10 gigabit rate there. And like we said, that's for the time stamping and keeping that data together. And we can expand this setup. So we had that first kind of basic setup, we started with this slide where we had the 3 radar units and the LiDAR unit. You can see here now we've added 2 cameras, 2 at the back and 2 at the front of the vehicle using those MDI links. There's also what we have as an intermediary device known as the NetLion. The NetLion takes automotive Ethernet and converts that to conventional Ethernet. And the reason for doing that, again, is for the time stamping, but automotive Ethernet is actually different than the conventional Ethernet. So the automotive Ethernet needs to be converted, and then we can again synchronize that data over the conventional Ethernet. And all of this is to get, you know, all these sensors lined up and synchronized in terms of time with a 1 microsecond or less discrepancy. So that's pretty good, I would say. You're looking at everything synchronized, bringing that into your algorithms and making sure the right decisions are made. And as the vehicle sensors increase and the setup gets more complex, the Scaptra system can accommodate that. So here is you know, a setup where actually 2 different Scaptra systems are being used based on the number of sensors in the vehicle, where we've expanded it to now have here 6 radars, a LiDAR, GPS, vehicle CAN, 4 cameras front and back, and we can bring in all that data and synchronize it and view it all at the same time, tag it for events that we want to monitor, whether they be right, left turns, vehicle stops, any condition that we can think of, we can look at that and tag it and go through that information over a given test sequence. So just kind of a zoom in here on that Scaptra recorder system. You can see the main unit there, which is got the storage brick. There's an onboard PC for the recording software that you can hook up with a mouse, keyboard, and monitor to have it in the vehicle for viewing and looking at the data. You know, there's camera links where we could add additional cameras to the system if needed, or tap into cameras that are being used by the vehicle. There's an independent power supply that we could use, or we could use the vehicle power. And there's a picture of that MDI link and how that comes up into the system as well. And here's the software. I don't know, Charles, do you want me to switch and show an actual recording we have?
Sure. Here, let me make you presenter.
Okay. I'll say show my screen. And so this is an actual recording taken with the Scaptra system. You can see there's 2 cameras, one set up here on the front of the vehicle, one on the rear, along with the CAN bus data here where we can see the packets coming in, and then the point cloud display from the LiDAR that's being used in this vehicle too. And you can see all this data is linked. I can kind of skip through the recording and play things. I can step through if I want to pause this. I can go through specific steps. I don't know if that's coming through okay, Charles. I don't know if you can see that.
Yeah. I don't think it's too much lag to the webinar.
Yeah, and it's kind of nice. When I set this up, I can have the objects and I kind of make this viewer for what I want to see. So you can see I've got the 2 camera views and the data where that's coming in on the system, along with the LiDAR here and the translator to the point cloud, and then the CAN FD. So as I kind of fill the ports available in that Scaptra system, I can make these different viewers to look at that data here. When I play through a file, everything again is synchronized, and I can view this, which is really nice.
Okay.
And then this data can, once I make sure everything's okay, I can pass it on to Tony and his team to work with it and compare it to some of their virtual data to enhance those algorithms going forward.
I think that's a good transition for us to make Tony the presenter to kind of expand on that a little bit more.
And hopefully you can see my screen right now.
Yep.
Yep.
All right. That was a great segue, by the way, Scott. Okay, in the background, you can kind of see that infinity loop that we talked about earlier. And what it is, again, on the left, we're kind of doing virtual. On the right, we're kind of taking data collection. There's a lot more going on. We're actually going to do, you see recorded data. It's an integral part right up there. And there's also some synthetic, but we're going to start feeding back around and doing a lot of functional safety, making sure we don't have hazards and things of that sort. As we fill this in, what we're going to see is that we're going to take recorded data, and if we go around, so we go down and to the left and up, we're going to get to massive verification. Okay, you see that on the left there, and we have metrics and KPIs. So how do we go about doing that? I just want to give you an example of that. It's a lot more detailed, but I'm trying to make this as simple as possible. So the first thing we need to do is, out of our collected data, potentially find situations that might be of interest. Close crashes maybe that happened, or that did happen, or something of that sort. So here's one, okay? We had a 3-lane road. There's a kind of a curve. And in the 3-lane road, you can see our car is in the middle lane. We have a car coming up on the left, so that's gonna not allow us to go into the left lane. And on the right, we have a parked car with a person getting out and another car coming up on it, and it's gonna cut in, okay? So this was sort of the scene that we found from collecting data, sort of a close call, right? Well, we can always change the scene. Well, how do we do it? We can't go back and collect data. We have to do it virtually, and that's what we do. So in our car, our Ego vehicle, we have a radar automatic emergency braking system. So it's going to brake if it thinks there might be an accident coming, and it's using both short range and long range radar. And what we're going to then do is we're going to change the speed of our vehicle and the speed of the cut-in vehicle. Now, by change, we're going to have to simulate it. That's the way we do it, because it's not really out there in the world. So we're going to change via simulation. And if we wanted to test the entire system, we'd have to run infinite number of tests, because speed is an analog number. So to test every single speed combination of the two would be infinite. But we want to try to do it in a smart way. And that's what we can do with our tool set. In particular, a software tool we have called HEEDS, which can figure out, let's say, a smart way to do less samples and get data. So let's see what happens when we do that. Okay, so on the x-axis, you can see our speed varying from 10 to 30 kph, and the cut-in or target vehicle going from 4 to 20. Okay, again, this space is, if it's an analog space, so infinite number of combinations, right? Well, we can't do that, so we're going to do a smaller set. In particular, 2500 is what we picked, and we use what's called a Latin hypercube, so it's not a grid that we're sampling. It's a little bit smarter than that. So let's see what we can glean from that. And the first thing we're going to notice is these red dots. These red dots are situations where the brake should have turned on, but it didn't. And so we ended up with a crash. The size of the red dot is how big the crash is. So these bigger ones are not good, okay? Maybe these smaller ones aren't too bad because we just got a small crash, but these bigger ones certainly are not. So let's take a look at what one of these looks like in the simulation. So we just went from one data collection to 2,500, and we found this situation, not a good situation, right? Now the next ones, these are all good. So we changed, we went from 1 to 2,500, and that entire swath is good. We put on the brakes and we avoided a crash. Now, how do we know that we avoided a crash? Because we can run it without the AEB system and we'd know. So here's something else that's probably good, and that's what's called mitigation. So it reduced the crash. So we would have had a bigger crash, and notice how it's a very small crash here. So those are good. Now these next ones, I've been in auto safety a long time. These are not good. These are what I call false alarms, which is slamming on the brakes when you didn't need to. So in this case, you can see the car on the right is not going to cut in. Why are we braking? All that does is potentially cause a crash. And then these last ones, these yellow diamonds, are really bad. By putting the brakes on, what we did was cause a crash. So had we not put the brakes on, we wouldn't have got a crash. So those, of course, are bad. So just, we'll see that right now. So don't put the brake on, we missed that. But because we did, we caused a crash. So when we're all done, what we see is, and then the blue, nothing happened, the blue dots. So what we see is this colored plot. So we went from one real close call to 2,500, right? Now what we found is between the purple, the red, and the yellow, we've got a lot of situations that are not good. So we just went from maybe this isn't a good thing to a lot of not goods. So we got to solve these. We got to change systems. We got to change algorithms. We got to do stuff. Maybe it's not possible in some situations. I mean, the car could just cut right in and there's no system on the world that can prevent the crash. So those are all things, though, that we can glean. So when we go from the real side of the infinity loop, get that data, we can then go here and expand our knowledge and also what we need to do to test and verify. Okay. And that is it.
Okay, great. We had a few questions throughout the webinar, but we have a few minutes left, and I think I'm gonna launch another poll. But if you had a specific question related to anything to do with this pre-scan 360 software and simulating a lot of these events, or something related to physical testing with Scapter, please feel free to and ask it now. But I will do, if you could let us know what you thought was the coolest thing you learned today. That would be great. Hopefully something caught your eye. Had a few people vote. Okay, 50%. I think I will close it in a few moments to give everybody a second. All right, I'm gonna close the webinar, the poll now. I'll share the results. Okay, pretty good. Tony, they really liked creating those virtual scenarios.
All right.
Yeah, you're today's big winner. The prize is you get a lot of questions, hopefully, from people who are interested in utilizing that technology. So I'm going to hide the results now, and I will just share our contact info. So if you would like to know more, take back the presenter for a second, Tony. Share my screen. If you would like to know more about that technology, that pre-scan 360, please reach out to Tony. There's his email address there on the screen. Or if you have some questions related to Scapter, Scott and myself are certainly happy to help you out or set up a demo if you're interested in getting involved in any data collection for your ADAS systems or your autonomous vehicles development. Well, I think that's it. That we have time for. It's almost 11, so I'll thank Tony for joining us today and presenting, as well as Scott. Appreciate you also joining today and presenting. Thank you everyone who attended. And like I said at the beginning, I will send out a follow-up email which will contain the slides that were presented today, as well as a link to recording this webinar if you wanted to watch it again or share it with a colleague. Other than that, I'll say I hope you have a great day, and we hope to see you at another webinar in the future. Thank you for joining us.
Right.
Awesome.
Thanks.
Thank you.
Thank you.
Thank you.